All right, let's look at another example. So let's say we have a matrix. And this matrix is a 3 by 4 matrix. 1, 3, 2, I'm going down the columns. -3, -9, -6. 5, 6, 0, 1, 1, 1. All right, so I actually want to look at the null space and find the basis for the null space. So let's remember what we mean by the null space. So remember, the null space is all solutions of the homogeneous system. Okay, so what's going to be helpful is if I row reduce this. So I'm going to put this matrix in RREF. All right, and so when I do, I get 1, 0, 0, -3, 0, 0, 0, 1, 0, 0, 0, 1. All right, so I row reduce this, and so if you think about it and set it up as a homogeneous system with zeros on the other side, we can solve for x1, x2, and x3. And x4. All right, so we know that our null space of our matrix A is going to be the span of this vector 3, 1, 0, 0. So 3, 1, 0, 0. All right, and if you want to see the work for how we solve this, it should be earlier in your notes somewhere. I think this was in 2.6. All right, so, well, if our span only has one vector in it, well, this is definitely going to be the basis element. So the null space of our matrix A has basis 3, 1, 0, 0. And so we always write it as a set. All right, what about the column space? Maybe I'll block this off so we can have it here. All right, so what is the basis for the column space of A? All right, so let's remember what the column space is. It's just the span of all of the columns of A. All right, so our column space, I'm going to write all of that out. All right, so this is the column space, and we want to find a basis for this. So we want to make sure, oh, I actually wrote that wrong. Sorry, guys. These should be separate vectors. My bad. There we go. So this is the column space. All right, so we want to figure out what is the basis for this. So we would like to assume that maybe all 4 of these vectors are part of the basis, but we have to make sure that the vectors that we include are linearly independent. So I'm actually going to do a small little proof first before we decide which elements are going to be our basis elements. All right, so let's choose any vector v in the column space of A. All right, so that means v can be written as a linear combination of these elements, of these vectors. All right, so we don't have to write these over and over again. For shorthand, I want us to write our matrix A as A1, that's going to be our first vector, A2, our second vector, A3, and A4. So we're taking our original matrix here and then just writing them in their column vector components. Okay, one thing that we should note is that A2 is actually a scalar multiple of A1. So these are related to each other. So let's take that note down. Note that A2 is actually -3 times A1. So that already tells us that these two are linearly dependent. So all four of these together will not form a basis. Okay. So if our vector v can be written as a linear combination of these vectors, so I'm going to call it C1A1 plus C2A2, there's nothing above the C, plus C3A3 plus C4A4. All right, if V is in our column space, it can be written as a linear combination of our columns. However, we know that A2 is actually 3 times A1, so I'm going to put that in there. So instead of writing the vector A2, I'm going to replace it with -3 times the vector A1. Okay. All right, so notice I have scalars multiplied by the same vector. I can combine that, so I can combine some like terms where I'll have C1 minus 3C2 times A1 plus the rest. Okay, so make sure you pause this to make sure that this all makes sense to you so far. All right, so what does this tell us? We are able to write V, which is in our column space, as a linear combination of only 3 of those vectors in the column, in our A. Does that make sense? So A1, A3, and A4, not all 4 of them. All right, so that means we can actually write our column space as the span of just A1, A3, A4. A2 is not necessary because it can be written in terms of A1. Okay. All right, so that means actually we only need 3 of them for linear independence. Let's make sure that the rest, we know the rest is going to span because we got our spanning set. So we can say 1, 3, 2, 5, 6, 0, 1, 1, 1 is a basis for the column space of A. Also, notice back up top at the original matrix when we row reduced it, notice that these our vectors we used actually correspond to our pivot columns of A. So it's actually the pivot columns of A that are going to represent our basis for our column space. So let's write that down.